Welcome. I'm hoping to hold one of these happy talks. I don't expect anyone to learn anything. So you can just relax, sit back and enjoy. I have too much content. I've been warned about talking too fast, but I hope that the number of slides is just because I have a style of skipping slides instead of having animations in my slide, because I can't figure out how LibreOffice does animations. So yeah, welcome to this talk. This talk is about customizing Qt, but it's also about how to adapt to custom hardware. I'll be talking about Cisco, which is my employer, where I work, a little bit about me, and what we do, like what devices that we make, customizations we make. I have 3 case studies I'd like to share with you, the real products that shipped and are successful, and what is under the hood, what we did. Really fun stuff, I think. And also some of the learnings that we had. And as tradition has it, I never managed to get to the learnings, so you just have to soak up. But yes, I work for Cisco. So yes, my name is Andreas Aardal Hanssen. I have a master and a civil engineering. It's just 6 months difference. I have both at the university in Oslo. I studied software. I've worked as a developer, self-employed and employed. I've been a manager, director, a team lead, and now I'm a principal engineer working for Cisco. So prior to work, I used to do open source development. So there's a IMAP server called Bing IMAP, which was a fun project that I did in a period where I was in quarantine, switching between 2 jobs, and I was not allowed to work on anything else. I also was a Qt developer. So I worked as a Qt developer working for the Qt for Trolltech back then. For 7 years, I was in Nokia. Best experience I have from Nokia is to say that I was there when Nokia happened. Nokia was terrible. I think everyone who knows what happened, who's there, can agree. Today I work in Cisco. I have a great time in Cisco. I think it rocks to be working on network devices, on security. I love the fact that it's green, as in video calling people means you don't have to fly. And we're also really successful both in software development in general, but also with our devices, and I'm going to share some of that fun with you. So what Lysaker Cisco builds is integrated video, audio, microphone products. So we do all the stack, from the fabric of the speakers to the angle of the rounding of the industrial design, to the PCBs, the layout, to the selection of chips. We go visiting vendors. I was in a meeting late night 2 days ago with NVIDIA, talking about how to get the whiteboard product, which you can see in the open area there, to perform well. And we have one software that we deploy across all of our products. We have one user experience that we deploy. We build continuously, and we deploy software straight onto customers' devices in production every day. And nearly everything is C++. And there's some web, and there's some Python, and there's some Bash, and there's some Java. So when we're selecting hardware, which we do, we literally pick every single chip that goes onto the hardware. We need to find chips that are high performance, as in that they've got video codecs that are relevant, that are 4K capable for encoding and decoding, that we have powerful display and graphics capabilities. We run 4K displays these days at 60 or 30 hertz. The CPU, that we have power for flexibility for the future, and also that there's suitable memory bandwidth on these devices. We also want these things to not consume any power, not have any heat footprint, to cost as little as possible, and to be supported forever. And then for this talk, the most relevant part is that we need software that can be customized, because we love customizing hardware. We change hardware to make it do what we want it to do. And so I think that when you're trying to reduce memory footprint, when you have battery concerns, when there's like immediate resource saturation, as in if you do something wrong, the entire system locks up, at least for a while, and there's heat dissipation issues, so you can't run the CPU for so long. That's really rough weather for any type of software. And I think we've been very successful in using Qt, not because it solves any of those problems, but because it runs on a system where you can have software running that does solve those problems. So I'll get to the point of that later on. This is the first of my case studies. I don't know if anyone here has used any Tandberg or Cisco video equipment, but this here is a very popular one called the Cisco SX80. And I was lucky enough to start in Cisco on the very first day that Tandberg became Cisco. I got involved with this project, and I met a team of engineers and managers and everything who were super inspired and wanting to dig into a very ambitious product. The Cisco SX80 is based on a Texas Instruments Netra chip, TI-8168. It has dual 1080p 60 HDMI output, so you can run 2 full screens on it. It's running an ancient GPU, PowerVR SGX530, which we overclocked, of course, to 2.7 gigaflops. And the first hurdle that we ran into with this product was that the vendor couldn't finish their software bundle in time. So we were wanting to use the hardware at a point where their software wasn't ready. And being, call it, arrogant as we were at the time, we were thinking, we can do it better than them, so we decided to run our own software, which means board bring up, which means device management, booting the kernel, all the software ourselves. This is the user experience that was expected at the time. So this is what people had been running on older products. And being as a person who works with graphics, graphics and user experience, coming into Cisco and seeing this, even though it was 2010, which to some people is a long time ago, this was terrible. We had a classic chroma key, like button on screen type of OSD menu. It was remote control driven, 16-bit color depth, no animations. It was all widget based, which for anyone working on Qt knows that it's for embedded devices. We don't do that anymore. There was absolutely no tests. And at the time, it was full of legacy. At the time, I thought it was full of legacy. These days, I'm older and wiser and know that it wasn't that bad. I've seen a lot worse. But at the time, I was like, what? This is shit. So there was no UX, no new UX. And by UX, I mean there was no graphics, visuals, design specs for anything new because our hardware couldn't handle it. No embedded hardware at that time could do what our designers wanted, because the only high-end hardware could do it, or could it? So the beginning of this saga actually was engineers who were passionate about graphics and pushed capabilities upward and challenged UX into actually building a world-class experience, which I thought was very inspiring. But this is NDC TechTown, so we're supposed to go down on the rubble. So don't worry if you don't know all the keywords here, but there was we had to build a custom interprocess communication, custom IPC between the A8, which is a ARM processor, and the M3s, which is a different kind of worse kind of ARM processor. There was something called a VPSS, which is a dedicated hardware chip, which was responsible for placing stuff on screen. It was also being controlled by custom software that we wrote, which is running on one of the M3s, and it operated on physical address spaces, which meant there's no MMU. So the A8 core Linux kernel was running with virtual memory, and the entire rest of the system was running with physical memory. So how do you get Qt high-level framework to render using a GPU onto these frame buffers? At the time, we were using Graphics View. I don't know if anyone's familiar with Qt. It's not so important. Today, we're also shipping software on the same device, and we're using QtQuick too. So hold your breath. Step one, we had to make our own display driver. And the way we did that was that we reduced the size of memory that was available to the Linux kernel. thereby releasing physical memory that could be dedicated to graphics. And then we wrote a kernel module that exposes that memory through a framebuffer device, or we called it a framebuffer device. In practice, it was just a device that allowed you to get the address of the physical space and also map that into virtual space. So we have a dev SM FB0 and FB1 for each of the two screens. And step number 2 was to visit Texas Instruments in India and then try to convince them to allow EGL initialize, which is like the first line of code you write whenever you want to do OpenGL or OpenGL ES, and allow that to pass even though there literally was no frame buffer. And they agreed on that, and not only that, but they agreed to merge that change that we did into their official software, which is published, which meant that anyone in the world who wanted to use these Texas GPUs for entirely off-screen usage, they got that feature, which I thought was pretty cool. It's not open source, but it's contributing to software which is made public, which I thought was cool. Step number 3 was that for each of these frame buffers that we had, which is 3 frame buffers dedicated in discrete memory for each of the screens, we had to create something called a pixmap surface, which is a OpenGL surface. And of course, Texas Instruments had support for something they called a native pixmap surface, undocumented. And they gave us a specification, which is in the right corner, for what struct you're supposed to pass to this API in order to give it access to precisely the type of memory that we had allocated. So it's not secret, it's just undocumented. That undocumented theme goes throughout this talk. Okay? Here it says in the Kronos official documentation for EGL create pixmap surface, at the bottom it says that this argument here, native pixmap, is implementation specific, which means it's not part of the spec. It's pretty funny. It's an official function which takes an argument which is undocumented. And then we had to make our own display driver. So what you can take away from this is just a few keywords, and the fact that it's possible. So what we did is we built a Q platform integration plugin. We overrided create to make our own platform integration. We made as many Q platform screen instances as we had frame buffers, as we had displays, too. We reused some parts of the internals of this platform integration framework, like the generic Unix font database, the native interface. We overrided a platform window, create backing store. We reused the event dispatcher. We pretty much just looked at what the other platform integrations did, and then we molded it to do what we wanted to do. The essential part is that we made our own GL context, which meant that we can take over the parts where Qt wants to start rendering, when it's done rendering, and when it's about to swap buffers, which is all graphics lingo for our low-level stuff, don't worry. So we built the plugin. The plugin needs to have a certain name. We just littered the code with printfs, modern debugging techniques. And then just watched our logs and traced and see what happens. And it took months to get this run, but it's no more than, I would say, 4 or 5 months before we had this thing running. And we, of course, all of Q platform integration is undocumented, so we have the source code. And having the source code of a framework like this, I think, is extremely valuable. And it's actually one of the points of this talk, that as long as you know C++ and you have like the guts, you can always walk the code and you can figure out how this works. And it helps to have somebody next to you while you're doing so. Okay, so step 5, integrating with this VPSS compositor. So now that we have a Qt application with a platform integration which is able to render into surfaces, we needed to get that hardware block which says what should go on screen to know when it should show each of these frame buffers which are in memory. And we didn't have any way to communicate, so what we did is that we built a very basic IPC mechanism based on pipes. And then we stored data inside of the header of each of these frame buffers with tokens to indicate which of the 3 frames in a triple buffer were current. So we got triple buffering. For those who know what that is, it means no tearing. It's very important when you do low-level development, and it's something you can take for granted when you work on on high-level frameworks. But we didn't have that, so we had to make our own. So this is pretty much what we got in the end, which I'm really proud of, which is a 60 frames per second tear-free analog clock. And I think it all really boils down to a lot of work for a little gain. And actually, a lot of the PMs were hating us for spending so much time on this. But the magic happened when this product hit the market, because what happened was there were pictures of it, there were videos of it, and people loved it, and sales loved it. We had our executives pull it up on screen in front of in events and brag about it. So what they were bragging about wasn't the 4K, the video encoding. It wasn't about all of these features which were part of the backlog. What they were bragging about was like a blue scale and an analog clock, which I think was pretty cool. And just for the record, this is the QML code, which is vanilla QML, because this is everything that's above that platform integration is vanilla Qt. So this is the actual QML code that takes to do that clock. There's a background image. There's an hour hand, which is semi-transparent. There's a minute hand, which is semi-transparent. We made a clock model, which is in C++, probably a different talk. But we bound, using property bindings, we bound the hours property of the clock to one hand and the minute to another hand, and applied a transformation, and that's sort of the clock. It's pretty cool. And it's all done using OpenGL. Whew, pretty cool. OK. Case number 2. Where's the clock, by the way? Do we have any? There we are. Now we're doing fine. So here's case number 2. Now, Cisco SX80 is a way more powerful platform. This is the angriest codec we ever made. The industrial designers, I don't know what they were thinking. Probably that everyone who works with internal systems and sysops are guys. I don't know. It looks really angry and masculine, I think. The product would end up looking like this, with 2 pan-tilt zoom cameras, very high-end audio and video capabilities, dual HDMI again, actually a third option for a third screen. And the issue with this one was that the hardware that was selected was a Tile GX36. And I don't know if anyone here has heard of a Tile Tilera. Facebook used them for data centers. It's a chip which is, at the time, 36 cores, which was unheard of at that time. But now, today, you could do 36 cores. Just buy it off online for your desktop PC at home. But this was for an embedded chip. It was quite unheard of. But the problem was it had no other chips. So there was just 36 cores. No display GPU frame buffer anything, because nobody needed it, and because the PMs who decided that we should go for this hardware didn't care about graphics, didn't care about user experience, and wanted that chroma key 16-bit crap to run on our devices. And then again, they were saying there is no display, there is no frame buffer, there's no GPU even now. Last time you had a GPU, this time you don't have one. But again, from engineering, we had I would say, we had a very strong push among engineers who were very passionate about graphics to get this thing up to speed. This is supposed to be our flagship. What do you do? Qt, for one, did not support TileGX. It still doesn't. All of our patches I just mentioned, they are publicly available, but we haven't upstreamed them. Up until like 5 years ago, there was a legal reason, and after that, I think this platform is actually dead. So I wouldn't bother anyone with wanting to keep this thing up to date. It would be us keeping it up to date, essentially. So I'm OK. It had its own GCC. That's awesome, like a fork of GCC, which was way behind all the latest developments. It had its own instruction set. So that means an assembly language that nobody knew. There was no docs online. You couldn't Google anything. It was all part of this big, fat manual that we got, which was full of mistakes. It had its own concept of atomic operations and intrinsics. There were none of the GCC intrinsics that worked. So if you wanted to do an atomic lock or a spin lock, you had to do it in assembly and yourself. And of course, for Qt, we had to do that. There's no display, as I said, no frame buffer. And there's 36 cores, which is cool. I mean, all of which we assumed could be available for graphics. So that sort of sparked the very enthusiasm in us. Can we make use of 36 cores? We assumed. So the first thing when you're porting Qt to a new platform, is that you need to investigate if you have to make something called a custom MK spec. MK specs are pretty much a combination of a QMake configuration and a platform header file, which define which C++ compilers you're supposed to use. As when you're using QMake, it's going to call your compiler, and you need to tell it how. You also instruct it how to do like default flags, paths, and libs, and all that. So we had to make it use the tile G++ instead of GCC and others. Then, some very short tips, I guess, that MK specs are hard to get right from the beginning, but there's usually inside of the Qt base MK specs folder, there's a comment folder, there's a lot of pieces that you can make use of. And usually all you have to do is like change a few flags. You'll usually get away with getting default settings. But one of the major things that we did is that we had to convince Qt that we had OpenGL, because we use QtQuick for the UI. QtQuick doesn't build unless Qt supports OpenGL. So we had to trick Qt into thinking that it had OpenGL in order to build the Qt declarative module. And so what we did actually is we made our own OpenGL library, which consists of all of the standard headers which are part of Kronos, so they're free license and so on. And the implementation looks like this. So we made every single function in the entire OpenGL 2.0 spec empty. So whatever you call, nothing. The only purpose of doing this is so that the test that Qt has to check if you have OpenGL support passes, because all it does is compile. If it compiles, it works, right? And then also the Qt declarative module links against Qt OpenGL. Qt OpenGL only cares if it links. I mean, there's no runtime tech to see if it's real, so we got away with that. Then we tried to build. So building Qt with a custom toolchain, I think, it's a very geeky interest I have. I think it's really cool, because what you do is you're compiling code which already is supported by 20 or so different esoteric platforms. And you'll be surprised at how often it passes. There's so much of that code that has been through so much rough weather, as in it's very, very compatible. We actually had, in the beginning, we had compiler errors which were typically warnings in third-party code. But actually, we had patches on those. We dropped them after a while because they ended up being fixed upstream. Many of the warnings were because of the Tilera platform, GCC, which was old, and Qt was new. So getting new code to work with old compilers. And those patches we never upstreamed, because who wants that? So also, there's some low-level things like iNotify support. On iNotify to watch a directory on Unix. That was different on Tilera for some reason. And the entire QAtomic we had to do ourselves. And it sounds like a great deal of work. Actually, in my team, I made an experiment. I picked the developer that I thought was least likely to make that QAtomic TileGX. Had no experience and only did high-level programming. And I was amazed at just the blooming that happened on that developer, because it was like 2 weeks later before the whole test suite had passed. So learning point to self as a manager being that never make too many presumptions about the capabilities of your developers with the right motivation, I mean. So anyway, Qt built surprisingly well. So porting Qt to a new platform, with our experience, it does not require a lot of work. And I think this is probably the worst type of platform you could port to, because nobody else is running it. Step 3, custom Qt. OK. So we wanted to use QtQuick 2, which is QML only. Sorry, it's OpenGL only. And that QtQuick 2 module requires Qt to support OpenGL. So in order to build the module, we had to pretty much stub the library, which I showed before. But in order to make it run, that's an entirely different matter, because then suddenly the Qt declarative library starts wanting to make windows and make graphical elements, and it assumes that these APIs actually work. And we can't have any of that. So what we did is that we found an internal class inside of QML in declarative called QSGContext. Internal as in, I think Qt developers were pretty fine with us using it, but it was just no documentation and no examples, so you're pretty much on your own. And we didn't really want to share that with Qt developers or anyone, but I feel like whatever. Do I want to dig into this? So QSG Context Factory is a class that is used to create QSG context. You can make your own. There's a way to intercept creating rectangles and images and glyphs for text rendering. There's a way to create a render context to take control over the actual rendering with render loops and with renders and so on. And there's something called Create Window Manager at the bottom. So the window manager is a QSG render loop. That's how it goes. This allows you to take over key APIs like showing and hiding and resizing and updating, which are, whenever a window is shown, eventually show is going to get called, and so on. And then because QtQuick requires OpenGL, there's certain requirements on a class called QOpenGL which you're expected to create. It doesn't have to work, but we created it inside of the show, and that sort of got us quite far along the way. But we had a feeling that we wouldn't get very far with this attempt. But we decided, why not have fun when we're first digging our hands in deep? So bypass the entire rendering. So when the application that we'd made had started up, on application started up, we created a vanilla widget. And vanilla widgets, regular widgets, are components that Qt is used to rendering. So whenever that thing gets exposed, it will trigger a paint and so on. So what we did is that we created a custom subclass of QWidget which took a pointer to the root node of our QML scene graph and used that to access the render node internally, and then paint event in the widget would then do a recursive descent drawing of the entire scene graph using our rendering code instead of OpenGL. And what we did is we used QPainter, which is the most stable software-centric painting interface in Qt. So we pretty much made a software painter for QML, but which bypasses the entire rendering loop of Qt declarative, of QML, QtQuick. Do I have until half or quarter past? Quarter past? Half again, cool. But the QPainter, that's another class, because QPainter sort of, that's a class that typically has platform-specific optimizations, and it's really fast on platforms like Windows, where you have a lot of, you have a very fast compiler with Visual Studio, but also Intel, which the Intel platform has very awesome vectorization and so on. But it still is a single-threaded painter, and we had 36 cores. So with that impressive platform, we were thinking, what could you do to Qt's software render that would make use of threads? Now, what I'm going to tell you now has been superseded in Qt. This slide and how we did software rendering for Qt has since been a part of Qt. So when we did this, there was no software rendering, but it became part of software rendering. Some of us talked, some of the people in Cisco talked to some people in Qt. Maybe we inspired each other, I don't know. But this is something that these days you wouldn't have to do. However, the threading part, I think, is still interesting. So let's study this example of a graphical interface with a background image. There's a dialog, some text at the top, at the bottom, and a button and a second button. This is a classic, very simplistic representation of a UI and what you might want to render using QPainter or a software painter. So what did we do? We came up with an algorithm that was suitable for threaded rendering. One of the things that it did, I would rather say the first thing that the algorithm did was that it would analyze the scene that was rendered, primitive by primitive, and then split the graphics into segments in the same way as an algorithm that's in old days was called S-buffering. But in a sense, there's like a vector, and there's a vector of scan lines, and for each of the scan lines, there's a vector of segments, and each segment contains information about how to render a certain strip of graphics. So this here would be an example of a geometric example of how you would represent that graphics as a sequence of individual blocks or segments of metadata that you could then do further processing on. So one scan line like this represents that block of graphics that you're seeing there, more or less. And it is a block diagram, but if you sort of stretch that out, if you do a walk like this, like this way, then you can see that this here block diagram can be represented in this way, where you have no overlapping. Now you can walk the scan line from left to right and draw things in the right order, and you'll get the same result. And that again can then be represented as a vector of segments, where the scan line itself knows its y, meaning its vertical offset, and its width and the stride of the frame buffer it's rendering to, and then each of the segments needs to contain like the colors and all that. So I'm losing some of you, but it'll all be over soon. So the cool thing about this algorithm is that it allows you to do perfect overdraw optimization, meaning that whenever you have something drawn on top of something else, which is typically a performance killer for software rendering, this algorithm allows you to walk through the scan line and remove everything which is drawn on top of afterwards. And that's very cool, because when you have a lot of complex graphics on top of each other, you have perfect obscurity culling, which I call it. You can draw from left to right with never touching a single pixel more than once. And I was about to say, and Patricia, who held the keynote yesterday and worked for us at the time, one of the most talented developers that I know, she did work on the optimizer here and discovered that it was a very complicated optimizer, which very often was not worth the time. It was one of the most groundbreaking things that we did at the time. So a lot of the performance that we actually have on the product today is thanks to her, not just because of the optimizer, but also because of the Tilera specific optimizations that we've done. So I'm saying this is only how it works in theory. That's not true. It actually does work like this, but it's more complicated because we had alpha blending and so on. But this is in principle how it worked. So custom painting in Qt requires you to go back to Platform Backing Store, which is one of the platform integration features. In the Platform Backing Store, you can create a custom paint engine, and QPaint engine has all of the drawing operations in it. This is an example of the API. Again, this is not something you need to learn. This is just to show that there is a class called Paint Engine in Qt, which has draw polygon and draw filling of rectangles and so on. And they're virtual functions. You can re-implement them, and then you can do what you want. This is how it looked in the end. I think that's pretty awesome, because it's a 60 Hertz analog clock. And spanning 2 screens. And how many threads did we end up with? That's a pop quiz. 2. But this is actually also a key point that I have, and that is that it's not that we just got 2. It's the fact that we managed to do dual screen 60 FPS graphics with only 2 of those cores. And I think that that's the learning point. It's not that poor us. It's that we, by doing this, we freed up resources on 34 of the 36 cores that were on that platform to do other things. Final case study now is the Cisco Room Kit. So the device that's out in the open area there's a Webex board. It's one of the most cool devices I've ever worked on. Still working on, we're doing generation 2 now. It's a wall-hung whiteboard. You can call people and share a whiteboard, and you can do whiteboarding 2 ways. There's an infinite whiteboard canvas, so you can draw like mega drawings. You can send emails as PDFs. There's a lot of fun stuff. But what's really cool is the graphics and what's happening under the hood. And not for the whiteboard itself, but for what succeeded the analog clock. Because after UX had done the analog clock, we started hiring a lot of UX people. They got really inspired and started making new designs which were pushing our platform farther and farther. Now that we had hardware rendering with OpenGL on the SX20 and this extremely customized but really powerful rendering on the SX80. So as the UX specifications got more and more complex, the screens ran in 4K, designers started coming up with this, which is sort of similar, and the key point here is not seen, but it's animations running in full screen. So not just an analog clock, which became digital, but animations that are running on the full screen. So what our designers used to send us these 16-bit nastiness. Sorry. Here we go. And I can't even do it with the console, so there you go. Okay, here we go. That's better. I can't see my mouse. There we go. Okay. So now this is what our designers started sending us. Hold on. Hello. Whoosh. Tap the home button or open your Teams app to start. And then in the background you see these balls going woo, and then somebody goes and touches the screen, and then the system transitions in to a wonderful home screen. So this is like what happens when you have, I would say, engineers pushing on the capabilities of the device, challenging UX, and UX coming back with something that the platform can't do. But anyway, UX was like, we want this animation. Developers go like, cool. But how does that look on a multi-screen system? And nobody thought about that, because designers typically think in a box. Sorry, no offense to designers, but that's sometimes they need help to think outside the box. The PMs were like, yeah, let's just do the same image on both screens, because PMs don't care. They just want the product to ship. And developers driven again, we were like, what? So we have one screen with this awesome effect, and the other screen should just be black. That's not good enough. And UX was like, what? Can we extend that animation to the other screens? And our answer was, of course you can. I mean, Qt only supports one screen for the QML scene. So if you have one QML QtQuick scene, only one screen. But who cares? How do you get QtQuick to render to multiple screens? So what we did then is that on application start, this time using a much more vanilla setup, we create 2 or 3 regular vanilla widgets on startup. And then we create, for each of those 3, we get the display subsystem to create contexts for us. So we're building on features that are in Qt from before, because Qt fundamentally supports rendering to any amount of screens. So all we did is that we just used the fact that we can create 2, 3 widgets in order to build upon what Qt has before. And then we created a QtQuick window, which is what you're supposed to create, that one window which QtQuick is supposed to run in, but we just didn't show it because we don't need it for anything else than the fact that it runs everything. We already have 3 widgets. With some magic, we should make it work. So then inside of our QML scene graph, we made 3 items. We declared them in QML, placed them next to each other, as in coordinate-wise, x, y, and z, x, y, and width and height. And then we used the geometry of each of these 3 items to build a matrix, a view transform, which we then applied to each of these 3 views that we'd made. And now we're leading up to being able to render the scene 3 times. So this is different from the previous hacks in that we're not completely bypassing rendering in one way, but we're bypassing rendering in a different way. So what we did here is that instead of, we jumped straight into the code in Qt where rendering actually happens, and then we installed a static global callback and a goto, which jumps over all of the Qt rendering code and then ends up down here. So pretty much saying, we'll handle this. And then what the callback does is essentially to render 3 times by borrowing the rendering context from each of our 3 views, making them current, and then rendering. We didn't need to do any recursive descent, new or our own rendering. We used what Qt had before. But the principle in the top left corner is very important to me. This is open source. This is the power of open source. If you want to make a change and you have an idea that it might work, then just do it. You can just jump in and make the code change. Don't be afraid. If the patch is ugly and you can't upstream it, that's fine. But even if you can't upstream it, you can talk to developers about it. There's an open governance model in Qt. You can discuss on open forums. And eventually somebody will probably say, that's not how to do it. However, here's one way you could do it. And maybe even somebody gets inspired to do it in Qt, or you could do it yourself. So rendering capabilities for multiple screens, okay, but here are these balls. Now, our designers decided to make balls that are not RGB. There are some esoteric parts of the color. I mean, they're not red, green, and blue. They're from very esoteric parts of the color space. So gradients in colors that are not in red or green or blue are really bad for RGB displays. And this is something that is very often pops up when UX meets the real world, because our displays are 24-bit RGB or maybe even YUV driven or CMYK. There's different color spaces which don't map to RGB really well, unless you're on HDR, which you are in HDR displays. You have a little bit more color space, but still, gradients on these balls typically create a lot of banding and aliasing effects. And when those are supposed to blend on top of each other, it gets so much worse. So first what we did, so this here is actual code, what you would see on that board if you press the home button for a few seconds and see that hello experience, is a shader effect. Now shader effects are, they're easy to understand for people who know OpenGL. And if you don't know OpenGL, it looks like black magic. But the principle is that you define 4 coordinates in each corner of a ball, and then you define using a vertex shader, and then using a fragment shader you define what the color should be for every single pixel inside of that rectangle. And the color, as we made it, is decided based on the distance of each pixel from the center of the ball, which would create a shaded blob. And then on top of this, we apply some dithering effects to get the banding to be right. So this here is how we do the actual shader effect of those balls in OpenGL, but we also have the SX80. So the SX20 GPU, now the Room Kit systems are using a GPU, an NVIDIA Tegra X1, quite cool GPU, but this poor SX80 in the middle, which is still supported, unfortunately has our custom rendering thing, which doesn't have shaders and all that. So what we did there is we just built a canvas-based one instead. And canvas in QML is just like HTML canvas. It's a 2D painting interface. We just drew the same ball using software. And it worked. And the funny thing is that old 2-core SX80 platform, it performs at like half of the performance of the NVIDIA one, which I think is quite impressive. It's very cool. Before I do that, I love the industrial design. I have to brag about that. It's not something I have anything to do with, but I just love how we have people working with, I keep repeating myself, I'm sorry if I did that, but like the corner radius and the texture of the cloth of the speakers, the alignment, there's a microphone array on some of our products, which means that we can position people based on when they talk, we know where they're talking from, which allows the cameras to track in on that person, so you can track the speaker. But this is 2 4K 60 displays. And this was recorded this morning. So Morten, who's a colleague, waves his hand, hello, and then look at the balls wander from screen to screen. I think that's pretty cool. Now, so this is like engineers and UX who had like a love child. This is fantastic, I think, Our PMs were like, what a waste of time. But our executives and our customers and sales have this thing on stage all the time. And they're showing off this awesome graphics, running Qt and QML, multi-screen and all that. A lot of engineering effort involved to get it working. And it's not on the backlog, but eventually it becomes like a key selling point. And of course, as part of this, also we got animations of all other kinds, but still. Five minutes, right? I have 15, but that's with questions, right? Yeah, that's fine. I only have 5 minutes more of content, so that's good. Why is it that we do embedded device or embedded systems development? There's different ways of looking at that. One of them is that embedded systems provide the absolute maximum of value over effort. And what that means is that you get, since the devices are cheap, but they're very powerful, you get a lot of value from them. And the effort one is like, well, I mean, sometimes you might actually spend a lot of effort. If you spend a lot of effort, I would say the value goes down. It's not a good deal. So the question is, how can you get effort to go down? Now, what I've shown now is that there's a lot of hacks you can do in order to get Qt to do stuff that it can't do. And if you're able to get Qt running on a device, which typically for vanilla cases does not require a lot of effort, then the effort goes down and you get more stuff done, which definitely increases this formula. But that's actually not my point. It's a deviation, because my point is that customers keep crying for new features, upgraded features, and so on. And this formula here only continues to generate value for the company if you're able to make it happen from an engineering point of view. And embedded devices are really tough. They're very constrained. But there's a rule that I usually apply. I usually talk about a lot, which is called the inevitable saturation. And that is that any type of technology can launch. And by that I mean I've been in this business now for quite some time, and I've seen projects launch, and I've seen projects fail, and you always end up with having some sort of a minimal viable specification that allows you to launch the product. But the problem is what happens after that. Because after the product is out in the customer's hands, the only way to continue making money or keeping that product out in the market and valuable is to make better use of it. But what we typically do is we clatter things up on top of it, and it gets slower and slower and slower. And you see that whenever you have like a set-top box, if you have like a get box, or you have a whatever they're called, Altibox box, they get slower and slower and slower, and then they go out, here's version 2, and then you buy that. And then it's fast, and then a couple of months later it's slower, and then it's slower, and then it's slower. And it's because of this rule. It's because new things start getting bundling in. The key is to find languages and technologies that allow you to continue to make use of the platform in a way that doesn't make the device slower and slower and slower. And for us, Qt has been a big success. The SX20 that I showed in the beginning was launched in 2011, and we had it live and shipping just until a couple of months ago. That's when we end-of-lifed it. And end-of-life then means we're going to be shipping software for 5 more years. It still has all of the features. Same with the SX80, and the same with the other platforms too. We're scaling down on a few things, of course, but the platform itself is quite lean. So on SX20, by taking software rendered classic UI and moving it onto the GPU, what we got was a first-class hardware-driven graphics, like modern graphics experience. But we also made use of a GPU chip, and we offloaded the CPU, which meant that the CPU could be used for other things. The CPU was near idling at a point until we saturated it. But the SX80, same thing. We managed to squeeze the GUI down to 1 or 2 cores, 1 in call, 2 outside call. And that meant that all the other cores were available for doing what we today do, is like facial recognition and so on. Pretty cool stuff. And today, that device out there is a 60 Hz 4K display. We're running on 1 out of 8 cores, and we're running at 15% CPU. And we're still getting squeezed for using less.
What kind of CPU is on the whiteboard?
The whiteboard is running a NVIDIA Tegra TX1. So it's the same essential chip as in the NVIDIA the switch, the NVIDIA switch, except NVIDIA has some customizations of their own that they put on that, but it's essentially the same thing. Today there's a TX2 and there's a TX3, which are just twice or 4 times as powerful as that one. But it comes with a Jetson, like an SDK and an eval board that you can get, which are really nice. So getting started with development is very easy. So, and I mean, Qt supports that thing out of the box as a single display, as with vanilla QML and all. So what we did is that we hacked the hardware in order to get 2 or 3 HDMI outputs on it, which it does not have. We made we made our own, like, we made a PCA, was it called, like, I think we used one of the embedded display ports and we upgraded that to be an HDMI port, and we did a lot of crazy stuff. So we do more with that hardware than it can do, and that's why we had to hack Qt to get it to make use of it. Can I have time for just a very quick? Qt is extremely customizable. You can either do it yourself, you can get consultants to help. Qt has consultants, KDev has, but there's also a community that can help. There's a very friendly community. You can hack the code yourself. There's also an open governance model. It's a wholly different talk, but you can actually push changes to Qt yourself, which I think is pretty awesome. I also think that we've had a lot of success with using an open source framework as a commercial vendor. Cisco has made a lot of money off of Qt. But, I mean, every single device that we ship with Qt every single device that we have made ships Qt with it. And in my opinion, personal opinion, I think that either you can use, like, if you're using the open source edition, you should contribute code. If you're not using the open source edition, or if you're not contributing code, I think you should pay for a license. But that's just me. So Cisco has allowed me, my team, and a lot of the other engineers to run off with cool ideas. And sometimes it's hard to manage, and almost always good things come out of it. If you're passionate about visual effects, why not just try? Give it a go. And if you run a demo and show it to somebody important, then they'll probably say, okay, that sounds cool, let's do it. If you want to get something done and there's a really ugly hack that can make it happen, go for it. It only turns bad if you lose control, but as long as you keep it playful, I think it's a good thing to do. And the final thing is that I think that developers today of any level of experience should not be afraid to dig in deep. And by digging deep, I mean, if you are willing to walk the path of the code, you can figure out how it works, and you can modify it. All right, so thank you for that. A little bit over time, but yeah, I'll take questions afterwards if you want. So thanks.